Hello everyone, my name is Po-Wei. Today I'm going to present the paper review for nonlinear pulse compression of a 200 mJ and 1 kW ultrafast thin disk amplifier as the final term project report. First is the outline for today. I will introduce the application for high energy and sub 50 femtosecond laser pulses. Then will be the abstracts for the paper. Then it will talk about the two main topics mentioned in this paper. One is thin disk laser and the other is multipass cell. It will include introduction, principle, experimental setup, and results in each section. Finally, it will be the conclusion for today's talk. As we learned in the course, the high energy sub 50 femtosecond ultra short laser pulses can facilitate the generation of high harmonic generation, terahertz generation, laser wave field acceleration, X-ray generation. With the abundance application for this kind of pulses, this paper demonstrates a high-energy laser source followed by a nonlinear compression stage that can compress the pulses down to 32 femtoseconds. Here is the abstract for this paper. A high-energy laser source consisting of an ultrafast thin disk regenerative amplifier followed by a nonlinear compression stage is presented. At the repetition rate of 5 kHz, the drive laser provides a pulse energy of up to 200 mJ with a pulse duration below 500 femtoseconds. In the low energy region, argon-based Harriet type multipass cell was used to compress 64 mJ pulses down to 32 femtoseconds. In the high energy region, helium-based MPC was used to compress 200 mJ pulses while maintaining compressibility below 50 femtoseconds. Here will be the introduction to thin disk laser system. In conventional rod laser, heat dissipation is always the major challenge. Since the cross-section of the rod crystal is small, it is very inefficient to cooling the rod, thus limit the repetition rate which it can achieve. Poor heat dissipation will increase the temperature inside the crystal and degrade the quality of the laser beam and may even lead to the breaking of the crystal. On the other hand, by using a thin disk with a large diameter comparison to its thickness, as shown over here, and let the face of the heat sink contacted to the crystal, the capability of heat dissipation will greatly increase and improve the repetition rate of the laser to kHz level. With two sides of the crystal coated with HR and AR dielectric coating, respectively, the reflectivity of the seed and pump radiation will be larger than 99.9% and thus keep the laser performance. Although inefficient pump absorption may happen due to few hundred micrometer scale thickness of the crystal, using a multi-pass pump arrangement, for example, 8-pass or 16 double pass of the pump, the radiation through this issue can fix. After all, thin disk laser is a good laser source that can generate high energy or high power laser pulses. Moving on, let's compare the characteristics of thin disk amplifier and Taisafa laser. There are three major differences. First is the laser material and the operation wavelength and the spectral characteristics. For laser material, for the thin disk amplifier, it usually uses the ND doped crystal. And for operating wavelength, the thin disk amplifier usually in the near infrared region and is around 1 micrometer, while Taisafa laser is around 800 nanometers. And for the spectral characteristics, one need to highlight it is the Taisafa laser has a very broad spectrum. Then why does thin disk technology overperform the conventional Taisafa laser? Is it about achieving higher pulse energy? The key lies in the superior cooling performance and efficient laser generation mechanism of the disk laser. Through the optimization of the surface to volume ratio, the thin disk laser ensures optimal cooling, surpassing traditional Taisafa lasers in generating high energy pulses. After knowing the advantage of the thin disk laser, let's see the state of the art of two laser systems. As we can see in the chart, Taisafa oscillator and Taisafa amplifiers can only achieve a power around 10 to 100 watts. However, thin disk laser or disk laser can achieve kilowatts level. With the usage of the thin disk laser, this paper arranged laser sources as shown over here. Starting from the regenerative amplifier, it used fiber-based commercial laser as seeding source with 969 nanometer diode bars as pumping source. Furthermore, in the amplifier, it uses two thin disk crystal in order to produce high gain and high power output. After amplification from the amplifier, a pulse speaker was used to trim the unnecessary parts of the pulse output from the regenerative amplifier, achieving a higher contrast and better pulse quality. Pulse picking is a technique that can implement a pocket cell with high voltage switch as the laser output port to trim unnecessary parts before and after the pulse, to eliminate the dispersion caused by the amplifier and pulse speaker. The authors then used a grating compressor to compress the pulse close to transfer limit pulse duration. And here is the results between using and without using the pulse speaker. As we can see over here, as using the pulse speaker, the pre and post pulse contrast on the nanometers timescale is improved to around 6.2 times 10 to minus 6, while keeping the output power roughly the same. These three figures shows the beam measurement after grating compressor at pulse energy of 200 mJ. Figure A shows the measured spectrum. Figure B shows the autocorrelation trace and the retrieved further transform limited pulse shape. The pulse duration is shortened as 461 femtosecond, and for long-term stability, the pulse length fluctuates merely within 2 femtoseconds during the 4-hour log. Figure C shows the measurement of the beam propagation factor m². In x-axis, it is around 1.4, and y-axis is around 1.3. As mentioned in the introduction, they aspire to reach higher pulse intensity, so they boost the output energy of laser source by simply exchanging the standard disk by thicker ones. Laser out power after thin disk amplifier boosted from 200 mJ to 500 mJ. Since the grating compressor do not support such high power, these two measurements results figures were measured at 1% attenuated laser. The output pulse duration is around 600 femtosecond, which is close to the Fourier transform limit pulse duration. The problem of not supporting such high power can be simply solved by change to large gratings. In the long-term test, the pulse-to-pulse stability is around 0.3% after recording over 50,000 consecutive pulses before the compressor at pulse energy level of 220 mJ. Okay, then we will go into the introduction part for the multi-pass cell. At first, let me introduce three common supercontinuum generation methods. They are multi-pass cell, multi-plate continuum, and hollow core fiber. Unlike the other two methods, MPC is more suitable to use to broaden the spectrum for high energy or high power due to excellent throughput in the range of 85% to 95%. Since this paper used MPC to create supercontinuum spectrum, therefore, for the rest of the report, we will focus on introduction of the principle, setup, and results of the MPC. The principle of the MPC to generate the supercontinuum spectrum can roughly sort it into three mechanisms. There are cell phase modulation effect, SPM, Kerr effect, and the plasma-induced ionization. Here, N denoted to the refractive index, and low 0 is the free electron number, while W represents the ionization potential of the nonlinear medium. Note that the plasma-induced ionization usually is the blue shift. When mentioning the characteristic of supercontinuum generation, SCG, there are two quantities need to know. They are critical power and B integral. Here the formula for critical power is shown over here. N2 is the nonlinear index of refraction of the medium, and N0 is the linear index of refraction. As we know, significant spectral broadening happens only when the laser power is larger than critical power. For gases, typical critical power is around 10 gigawatts, and for condensed medium, the critical power is around 10 megawatts. According to the critical power of the gases and solids in the table, we can know that gases can run at higher powers without causing optical damage. Next, B integral is the nonlinear part of the phase shift accumulated at the peak of the pulse during propagation. Here, L denoted as the medium length, I of Z represents laser intensity at position Z, and I0 denoted as the laser peak intensity. Note that a higher B integral indicates a higher capability of spectral broadening, and for each pass, the recommended B integral should be less than 3.14 radian. After introducing the principle of spectral broadening, let's take a closer look at the components of multi-pass cell. It consists of three basic elements. First is the curved mirror at two sides. The laser spot will hit the edge of the concave mirror and bounces between two mirrors for several times and focus in the middle of the cavity. The orange dots on two sides of the pictures represents the spot that the laser hitting the concave mirror at different times. In this technique, the nonlinear medium is placed inside the cavity, which preserves the beam parameters and acts as a discrete waveguide. Second component is the in and out coupled mirror, over here and over here. Those two mirrors guided the light in and out of the cavity. The green dots represents the first time and the final time that the laser hits on the concave mirror respectively. Then third will be the nonlinear medium. Nonlinear medium can be a solid or a gas. The solid will be placed at the center of the cavity, while the gas will be filled inside the entire cavity. As the laser focuses around these nonlinear materials, the cell phase modulation and Kerr effect will occur and thus broaden the spectrum. Therefore, we can calculate the critical power and then decide the multipath cell as we want. This is an animation of multipath cell. It is composed of two concave mirrors, just like a laser resonator. And nonlinear material will be placed inside the cavity to cause the nonlinear effects. The light will be focused at the center of the cavity and have high intensity, which will let the power to be higher than critical power and cause strong nonlinear effects and obtain strong spectrum broadening. These figures come from the Laser and Photonics Review letter. It collects all papers using MPC technology before 2021 and compares their output pulse duration and output pulse energy. The orange area is gas field MPC and the dark green area is the bulk MPC. We can see that under the same pulse duration, the pulse energy of gas MPC will be higher than the solid MPC. This also confirms that this paper needs to use gas as the nonlinear material of MPC because of its strong input pulse energy. From the authored pre-studies, they expect ionization and optical damage of the mirrors when input energy larger than 70 millijoules. So they scaled down the energy to 64 millijoules at a repetition rate of 5 kHz. After entering the chamber, the light will pass the refractive telescope T1 over here, which is used to adjust the beam size, and the concave mirror M1 is used to guide beam into the cavity and match the mode of the cavity. The MPC consists of 23 identical mirrors with a diameter of 1.5 inch and an ROC of 5 meter. Arranged in a circular Harris type configuration, the cell features two circular mirror arrangement composed of 12 and 11 mirrors separated by 9.9 meter. The overall outcoupled energy is as high as 63.3 millijoule, highlighting the outstanding transmission efficiency property for MPC. Then the beam is guided out of the chamber after collimation by the second concave mirror over here, and beam size magnification of T2. To avoid both nonlinear interaction with air and damage on the following chirp mirrors, they performed the pulse compression at 1.5 millijoules after attenuating the beam by an uncoated wedge. Then the beam went to the chirp mirrors for pulse compression. The principle of the experimental setup used in helium-based is the same as the argon-based MPC. There are only differences on parameters such as pulse energy, which is up to 156 millijoules, and the refractive telescope magnification for T1 and T2. The spectral broadening was stimulated by solving the extended nonlinear Schrödinger equation with a slit-step approach. The paper conduct two simulations for argon-based MPC and helium-based MPC. For argon-based MPC, you use 64 millijoules and 500 femtosecond pulses with the argon pressure of 90 millibar. And for helium-based MPC, you use 200 millijoules and 500 femtosecond, 400 millibars helium pressure to do the simulation. And the results show that for argon-based MPC, the on-axis beam integral for single pass is around 2.6 radian, while the on-axis beam integral for 24 passes is 62.4 radian. The estimated minus 20 dB level bandwidth is around 101 nanometer. On the other hand, helium-based MPC, the on-axis B integral for single pass is around 2.1 radian. On-axis B integral for total passes is around 50.4 radian, and the estimated minus 20 dB level bandwidth is around 106 nanometer. And these two figures shows the simulation result for helium-based MPC. Another important result in this is the pulse width versus the number of passes. As shown in this figure, the FTL Fourier transform limit pulses for two cases will saturate around 30 femtoseconds after 20 number of passes. Our team has also used the same parameter of helium-based MPC and simulated using MATLAB. The left-hand side is a frequency domain, then the right-hand side is a time domain. The first row is our simulation results, and the second row is the paper results. And surprisingly, we can get similar results as the paper results, which proves that this method is feasible. After the simulation, here I'm going to introduce the experiment results for argon-based MPC. The SHG frog retrieval error is around 0.47%, and the primary pulse containing more than 85% of the pulse. And the pulses can be compressed from 461 femtosecond down to 31.6 femtosecond, which shows a compression ratio around 15. And the laser peak power can reach around 1.6 watt when compressed and 64 millijoule. And the measured m square in x-axis and y-axis is around 1.4. And for the homogeneity values of the output beam, it exists 97% within the 1/e squared diameter, which demonstrating the MPC does not alter the beam quality. And also in this figure shows the Fourier transform limit of the beam evolution in x-axis and y-axis are similar, which suggesting isotropic beam properties. And the FTL over 1 hour of operation is around 37.4 femtosecond plus and minus 6.5 femtosecond, and the peak to valley deviation is 2.9 femtosecond, which suggesting a consistent supercontinuum pulse generation. For helium-based MPC with input pulse energy around 150 millijoules, the SHG frog retrieval error is 0.57%. The pulses can be compressed to 38.8 femtosecond with 14 refractions over the chirp mirrors. This shows a compression ratio around 12. The primary pulse containing more than 85% of the energy. With the energy transmission around 96%, the laser peak power can reach around 12 to 3.3 watts. And the measured m square in x-axis and y-axis is around 1.46 and 1.37. And the homogeneity values of the output beam is larger than 92% within the 1/e squared diameter. This indicates reasonable spatial spectral homogeneity. And the FTL of the beam evolution in x-axis, y-axis are similar, which suggesting isotropic beam properties. And for helium-based MPC with the input pulse energy around 200 millijoules, the SHG frog retrieval error is also around 0.57%. And the experiment side, the guys can observe the onset of the ionization, which indicates a severe blue shifting in the spectrum, and the pulse can be compressed down to 45 femtosecond with 14 refractions over the chirp mirrors. And for the spectrum part, we can clearly observe the blue shifting. And for temperature characterization reveals uncompensated third-order dispersion. The measure m squared in x-axis and y-axis is around 1.5 and 1.47. And here's today's talk's conclusion. At 5 kHz, the thin disc amplifier delivers a pulse energy of 200 millijoules with a pulse duration around 50 femtosecond and a beam quality around 1.4. By using an additional pulse picker stage, the pre and post-pulse construct on the nanosecond time scale is improved to 6.4 times 10 to minus 6. Further increase the thickness of the disc, the pulse energy can reach 550 millijoules with a transform limit pulse duration around 602 femtosecond at low energy. Using argon-based MPC, they spectrally broaden the pulses with pulse energy of up to 64 millijoules and 5 kHz at the optical efficiency larger than 99%. With proper dispersion management, The argon-based MPC can compress pulse with a pulse duration of 461 femtosecond down to 32 femtosecond with an excellent spatial spectral homogeneity larger than 97%. Broadening at helium-based MPC can generating high air energy up to 200 mJ and 1 kW of average power and transmission of around 96%. Compressibility of the broadened pulses to 45 femtosecond is shown with a preserved beam propagation factor of m² less than 1.4 and a spatial spectral homogeneity of larger than 90%. Thank you for listening.